Hello, welcome back to Cracking the Cryptic, and we got a puzzle in from Mateo99, who is from Argentina. So, vamos, Mateo. But now, Mateo called the puzzle Cantor's Blue, and in his version, all of the arrows were blue, and the cages were blue, and indeed the palindromes were blue. But those aren't the kind of standards. So I've retained the title, but I've put the puzzle through Sudoku Maker and Sudoku Pad, and here we have it in a form where I will understand these markings better, and maybe you will if you've followed us over the channel. If you have done that, you will know some of our standard rules, and you will be a prime candidate to purchase one of our apps like Arrow Sudoku or Killer Sudoku or Classic Sudoku 2 or the Worms, which are great fun. They have super puzzles in, some of them by absolute wonderful creators, and we recommend them highly. Now, there's also our Patreon where you can get a Sudoku out on the 1st of every month. Yes, coming up. And also, of course, there are other videos on Patreon, gridogram and connections and some cryptic crosswords, just for your delectation. Do give Patreon a try, and give this a try. This is Cantor's Blue by Mateo99. I believe it's pretty hard, but we will see. I'm going to go through the rules. Normal Sudoku rules apply, so 1 to 9 will go in every row, column, and 3 by 3 box. Digits in a cage don't repeat. Well, I think that's clear from Sudoku rules, and they sum to the total shown. So those 3 will add up to 8. Digits along an arrow sum to the number in the circle, so those 2 will add up to that one. Digits along a grey line read the same forwards and backwards. So these grey lines are palindromes. Those 2 digits will be the same, so will those 2. Very simple rules, quite short palindromes and arrows. So although there's a few of them around, I think this might be difficult. Let's get cracking. You can try it on that first link under the video. Okay, well, this digit is adding 3 separate Sudoku digits that are different from each other. So it's at least 6. And given the given, it's not actually 6. This pair is either 9, 5 or 6, 8. The 8 cage must have a 1 in it. The 12 cage must have a 1 and a 2 in it. The 10 cage has either a 1 or a 2, or both. That's a bit less interesting. I mean, none of these digits in the 8 or the 10 cage can be 8 or 9. Oh, this digit is going to have to appear in box 2, not on its own arrow, and not in those cells by Sudoku. So it does appear on one of these arrows. The trouble is this is a 1-cell arrow, so even a 9 could be on the actual arrow bit. Okay, I'm not getting very far here. I'm wondering straight away, are we going to have to come up with some interesting technique? And by interesting technique, I am thinking about set, and I am thinking about set for a very good reason, and that is lots of these arrows move away from their circles in a diagonal fashion. Now you might wonder why that's interesting, and I will try and explain. I don't know if I'm right, but there's a chance I am. So I am going to highlight this row in green, and very tempted to highlight all of these 3 rows in green, because these have the bulk of, I'm ignoring the arrow in box 9, these have the bulk of the arrow cells on, and not the bulb cells, not the circles. And I find that interesting. Then I'm going to highlight this in a different color. Let's choose pink and this column. And now we've picked up 2 of the 4 of the circles. So you don't always highlight the same number of rows and columns, as it were, or the same number of sets of 1 to 9 against each other. But I am tempted to add this row into the pink. And that would bring the palindrome into play as well. Yeah, I'm going to. Okay, so each set that I've highlighted so far is a set of the digits 1 to 9. Row 1 must be, row 3 must be, row 5 must be. Column 7 and column 3 must each be a set of the digits 1 to 9. If I highlight this row as well, and this might be a mistake, then in pink, as long as I count these 2 cells twice, because they're in both a column and a row, I have got 3 sets of the digits 1 to 9 highlighted. The same is true in green. And what I'm now going to do is try and cancel off totals against each other. So first of all, I can start with these 6 cells, which appear once in pink and once in green. If I remove them from my imaginary Scrabble bags of 3 sets of the digits 1 to 9, then I have got the same totals left over. Certainly, in fact, the same numbers left over at the moment. But what I'm now going to do is remove these green and that pink, which adds up to the same total by virtue of the arrow. And then I'm going to do the same with that one and with this one, which requires me to reduce that down to counting once. And there's this arrow as well, and this arrow, and this arrow. And now what you're beginning to see is the pink cells I'm going to be left with. Now the reason I included this pink in was so that I could get rid of those greens. And I thought I could also match these 2 cells on the palindrome off against these 2. I think I can. I don't know if this is worth doing, but I'm going to try it. So that is now counting once only. So the cells I have highlighted in green add up to the same total as the cells I have left in pink. And I know something about the total of the cells in pink. I know that these add up to 10 and these add up to 8, and that's 18. In green, these add up to 14. So I could do an equation for the remaining greens against the remaining pinks. If those add up to 14, these add up to 4 less than the total of all these. 4 being the difference between 14 and 18. I don't think this is that wonderful, so let me go back a bit. Maybe I shouldn't have got that 3rd pink row. Now at this stage, I know there's a 45 difference because I've got 2 sets of pink and 3 sets of green. So green must add to a set of the digits 1 to 9 more than pink, and a set of the digits 1 to 9 always adds up to 45. So let's just do it from here. There's a 45 difference. Green is 45 higher than pink, and then I'm going to remove these colors and these and these. And obviously, yeah, the individual ones that match, that are both green and pink. Right, and I'm left with this grouping. Now what I can do is convert these cells which are green, and adding that much to the green total to being these two cells instead. Yes, that's good. And there's going to be some equation relating to that in the end. Oh, this cell is always the same as that cell. Oh, I see. Yes, yes. So I can delete those against each other. It's not that the palindrome pairs add up together. It's that the individual cells match. That cell is the same as that cell. So I can move that green into there. Oh, this is looking good. This is looking good. So now I know, I highlighted 3 green rows originally. My green area adds up to 45 more than my pink area. And my pink area adds up to 18 plus that cell. Now, my green area, if I was to make these green and pink, yeah, beautiful, beautiful. I get it, I get it. I'm adding those to both green and pink. And now I'm finally going to subtract the extra 45 out of green. Bingo. And now I'm matching. I've got a little Stonehenge here of pink. I know exactly what it adds up to because I've got cage totals, which is 30. And that must be the same total as these 4 cells because I've matched all the time, pink to green. And that is set theory in an absolute nutshell. Now, that means that these 4 green cells in the top row add up to 30. That is the maximum for any 4 cells. They have to be 9, 8, 7, and 6. So there's no 5 here, no 9. That's an 8, 6 pair. This is a 9, 7 pair. This circle now becomes an 8, de facto. And we're off. I think that's the break-in. I'm really, really confident that's the break-in. And I'm sorry if it took a bit of manipulation to get to that. I'm not as fluent as Simon with set theory, but we got there. Now, one of these cells is an 8. That's Sudoku. I want to try and do a bit of Sudoku now. One of these cells is a 6. It can't be that one because that would clash on the palindrome. So one of these 2 is a 6. And since if that's a 6, that's a 6, one of these 2 in the column is now a 6 as well. This is a set of 1, 2, 3, 4, 5, and the 1 must be on the arrow, along with a pair that adds to 7. Oh, gosh, I mean, you know, set theory gives you a start. It doesn't complete the whole puzzle. But it does give you a start. Now, one of these digits, if that's an 8, that's an 8. But if one of these is an 8, there's also a 1 here, which there can't be because there's a 1 on that arrow. So they can't have an 8. That is an 8, and now that's an 8. Now I've got 3 8s in the puzzle. I'm doing that well. One of these is an 8, and it can't be on the palindrome because that would throw it into a cage, which can't be made to add up to 10. So 8's in one of those 2. Now, nine can't sit on that arrow, so 9's in one of those cells. 9's also in one of those. 9 can't be in one of those cells and must go here in row 3. Now, can 7 be here? The only way 7 can be on this arrow is if this is 7, 2. That would have to be 1, 3, 4. This would be 9, 5. This would be a 9. It is possible. It's quite constrained. Is this arrow doable? Not really yet. This end cell on the palindrome now can't be 6, 8, 7, or 9. I'm daring enough to pencil mark that. We've got a triple adding up to 8 here. There is a sort of a colouring thing with 8 pairs, or 8 trios one could do. Because that cell, since this group adds up to 8, these two will add up to 7 and be either a 2-5 or a 3-4 pair. And whichever pair they are doesn't appear in this cage because that digit can't. And that means that this cage is made up of exactly the same digits as this cage. So I'm going to make them all pink. I'm going to get rid of the green colouring because it was all in the set and we dealt with it. It was exciting and we found it all. So that pink cage is made up of the same 3 digits as this one. That's my claim. Now, I was going to say where's 1 in this box? But since I can't rule it out of this cell, maybe I can. This gets quite interesting. If that is a 1, then the 1 in the 12 cage is forced into this cell, which also puts a 1 here, by the way. That would make this 10 cage. The only way you can make up a 10 in 3 digits without a 1 is 235. So this would have to be 235. That would make this digit be a 4. That would make this one be a 3. This would be 125. It's all founded on a 1 here, which is a 1 here. There's a 1 here. Okay, I haven't actually managed to... there would be a 1 right here. And a 1 here. Let's just keep on dotting these around the grid. There'd be a 1 in one of those cells. Obviously one of these two. That one because of the tiny palindrome. And can't be on the palindrome here because it would repeat in box thingy. So one of those two. Oh, bother, I didn't have the thing held down. Okay, for that to be a 1, we do get a vast amount of 1s placed around the grid. It ends up being in one of these two and there. One of those two and there. These would all be the 1s, the highlighted cells. I can't actually say that that's not the case. Which is a pity, because if I could take 1 out of this cell, I'd know there'd be a 1 in one of these two, I think. But there we go. You get what you can. These two circles are the same as the sum of these 5 cells in box 2 on their arrows. And they have to add up to at least 15. And their total can't be 16 because they can't use a 6. The only way you can get to 16 in 5 cells is 1, 2, 3, 4, 6. So if it's not 15, it's 17 or more. And that's what the total of these two circles is, either 15 or 17 or more. Now this digit must be 7 or 9. And these cells either do add up to 15 or 17. And if they're 17, they're definitely 1, 2, 3, 4, 7. And if they're 15, they're definitely 1, 2, 3, 4, 5. So the only possible digits missing are the 9 and 5 or 7. So this 9 going in one of these cells is going with a 5 or a 7. Now, it can't be going with a 7 because there's a 7 in one of those cells. And if we were to put 7 in one of these cells, this circle would need to be 8 or 9, which it can't be. So this 9 is going with a 5. There is a 7 on this arrow. It must be 7, 2 equals 9. This group doesn't have a 2 in, and therefore doesn't have a 5 in. This pair is a 2, 5 pair in row 1. This is a 1, 3, 4 cage now. And 5. Oh, I was going to say 5 must be on this arrow. I haven't got that, actually. That's not necessarily true. 2 has appeared here, so this digit on the palindrome is not a 2. And these ones are selected from 1, 3, 4, 5. giving a total here. Well, we're not allowed 6. Could it be 7? 4, 5, or 7? Not 5 because of that pair. 4 or 7. So this is either 1, 3 or 3, 4. And definitely uses the 3 and definitely doesn't use the 5. Now this can't be a 3 on the end of the palindrome. And this is either 1, 3, 4, 6, 8, 9, 5. Oh, 5 now in this box has to be there because of that 5, 9 pair. So we'll put 5 in there, 2 in there. And excuse me a moment, I'll be back in a second. Sorry. Sorry about that. Right. Hopefully I am still recording now. I think I am. Let me just check whether I am. Yes, I am. Okay, good. Right, now we've got this 5 and this 2. 6, that 5, that's what we just got. Right, this cannot contain 2, 3, 5 now, this 10 cage. And therefore it can't avoid having a 1 in it. As I said before, the only way of doing 10 in 3 digits without a 1 is 2, 3, 5, and that's now impossible. So there is a 1 there. There is not a 1 here, but there must be a 1 in this cage. Now it's in this box, and that can't be a 1, and that's on the old palindrome again. And is a 4 or a 5. Actually, let's just have a look at this palindrome digit, which can't be 2, 8, 1, 3, 4, 7, 9, and therefore is 5 or 6. Can either of those be ruled out? I can't see why. Interesting, though. It doesn't necessarily mean one of those is 5, although I suspect that will be the case, but no, it doesn't mean that yet. Right. Now, there's a 1, there's a 3 here. I'm glad I pencil marked that. There's a 9 here, 6, 8, 5. These are from 1, 2, 4, 7. And 3 is over here somewhere. Okay, that doesn't help. What about this 10 cage? It's not 1, 4, 5. It's either 1, 2, 7 or 1, 3, 6. Oh, this digit repeats here. And this is from a fairly select group. You can only put 1, 2, 3, 4, 5 or 6 into a 12 cage. Ooh, that's almost ruling out. The 12 cage has 2 possible fills. It's either 1, 2, 4, 5, and I was wondering if that had become impossible, or 1, 2, 3, 6. Anyway, let's go back to the simplicity. This can't be a 5 or a 1. This is 2, 3, 4, or 6. And it repeats on the palindrome and must repeat in one of those cells, whatever it is. If this was a 1, 2, 4, 5 cage, that digit would have to be there. And would be a 4. But if this is a 1, 2, 3, 6 cage, I'm not quite so sure. Okay, let's have a look at this digit for a moment. It sees 1, 3, 4, 2, 8. In fact, in the column, this sees 7 and 9. This digit is 5 or 6. Well, that is incredibly useful both in the column and the row. So first of all, in the row, a 5, 6 pair there makes this a 4. And that makes that a 4. And these are now a 1, 3 pair, and that makes this a 4. And these are now a 2, 7 pair, apparently. These have become a 1, 3 pair. I'm taking out my corner marks. These are a 7, 9 pair. So this circle now is only 7 or 9. 4 is now ruled out of this cell. And now we know, therefore, this is not a 1, 2, 4, 5 cage. This is a 1, 2, 3, 6 cage. I'm going to take out the corner marks. This, oh, it's only 1, 4, 5 that's been ruled out. It could still be 1, 3, 6 or 1, 2, 7. 1, 2, 3, 6 there, 7, 9 pair there. The only possible digits here are from 4, 5, 8. And this one on the perimeter can't be a 4. because of that. 2, 3, 6. I don't know if that tells me about these. Let's just add up this column. 5, 4 and 9 is 18, plus the 10 down there is 28. Since, as we had to do for the set earlier, we know the sum of the digits from 1 to 9, which populate this column, is 45. These must add up to 17. That's not as helpful as I was hoping. That could still be a 2. There is a 1 here. In fact, 5 and 7 in this box have to be in this row. And now that digit can't be 7. So that's a 9. This is a 7 in the circle. I'm very tempted. Oh, we can't have a 5 on the arrow. I was going to say there's so much possibility of a 5 in those cells. I'm tempted to say there's no 5 on the arrow. But we know there's no 5 on the arrow because of 5 in this box. So this arrow is either a 4-3 pair, and we would know the order, or, a bit more likely, a 1-6 pair. 2 in the box has to be in the top row. This digit now sees 9, 8, 4, 5, and 2. It can't be 1 by virtue of its arrow, so it's 3, 6, or 7. And there is a 7 in one of these 3 cells. If it was a 3, this would be a 2-1 pair. That would be a 4-3 pair. What did I say these 3 had to add up to? Can't remember. Recomputing. 17. So if that was a 3, this would be a 6, and that would be an 8. 8 is key. 8 can't be in these cells by Sudoku, so it's in one of those 2. And the 8 in this box is in one of those 3, and it can't be on the arrow with those possible circle digits. So 8 is there. And now these have to add up to 17, including an 8. So these outside 2 add up to 9. And do you know what? I can't remove any one of those digits in that calculation. Nothing has really changed. That's peculiar and rather irritating. Okay, if that's a 6, this is a 4-2 pair because it's not allowed to hold a 5. If it's a 3, it's a 2-1 pair. If it's a 7, then I don't know. It's a complement of that. This digit was going to repeat in one of these. Could still be 2, 3, or 6. This arrow can't use 1, 3, or 4. It's got to use a 2 and either 5, 6, or 7. And it's got to sum, therefore, to 7, 8, or 9. Oh, we've got this we've got other palindromes are barely used. That digit repeats here and must repeat in one of these cells, so it can't be 2. This digit repeats there and in one of those cells, so it's selected from 1, 3, 4, 5, 9, 2, or 7, but here and here it can't be 4 or 9. That's not so helpful. What about this 8 cage, which wasn't even in the original Stonehenge of the set? Okay, that 8 cage makes me ask, where does 9 go in the column? And I can suddenly answer that. It can't go here because of that, so it must go in row 2 with a 5 next to it. Now, this can't be a 5 on this palindrome again. In fact, these cells are now being selected from something that can go in up there. 1, 2, 3, 4, 7, 9, but they can't be 4 or 9. So they're 1, 2, 3, or 7. I'm desperately hoping the pencil marking is going to lead to something revelatory, but I'm not really closing in on that, if I'm honest. So back to this central column, where now we always knew this 8 cage couldn't have 9 or 8 in it. It also, no, not true. It can have 7 in it. I suppose those two cells add up to 8 for palindromic reasons. Is that useful? Not obviously. Okay, let's go back over here. If this was a 6-1 pair, that's 5, 8, 4. This would have to be 2, 3. If this is a 4-3 pair, that's a 5-8 pair, that's a 6. This would be 2-1. So this is either 2-1 or 2-3. This digit on the palindrome is going to repeat into one of these 3 cells, and it won't be the circle. Oh, what did I say earlier? One of these was a 2. I was thinking of trying to use that in X-Wings, but I didn't really take the thought any further. Not quite sure how to, actually. Oh, look at this row. 1, 2, 3, 6, 7. So these are from 4, 5, 8, 9, but that doesn't include 8. They must include 9, however, in the row. Interesting. Again, interesting. But again, not conclusive. Still work to do. Those 2 are the same and appear in one of those 3. 1, 3, 6 here would lead to that being 2 and that being 7. I don't know. Okay, let's come back to the 8 cage. Maybe there is info there. If this was a 1-7 pair, that would be 2. These would be 3, 6. That would be 4, and we would be putting 5 here. Oh, 5 has not been pencil marked into this column yet, apart from potentially here. So either this is a 3-5 cage, or that's a 5. Now, if it was a 3-5 cage, does something break down? This would be 1 or 6 repeating. That would be 1 or 4 at the top. Ah, where does 4 go in the column? It can't go in the 8 cage, not because it's not big enough, but because it would have to repeat. So 4 in the column has to be at the top. And now there's a 4 in one of these 3 cells. And that's probably not going to go any further. But still, we have reduced the population in the central column by a little bit again. And we know this is either 3, 5 or that's a 5. Maybe I should think about, can it be 2, 6? That would be 1, 3. That would be 5. That would be 7. Now I feel I'm not going to get any further. If that was just to establish this 4 at the top. Oh, let's get rid of pink. It's not really doing anything anymore. 1, 3, 4 there. 5, 6. That digit is repeating into one of those cells. Don't know whether it's 5 or 6. Let's have a look at this row. 9, 8, 4. There's definitely a 2 out to windward here. So where's 2 in this box? It's on that arrow. No, hang on, it could be in that cell. Oh, calm down, Mark. Bother. Well, I nearly made a huge ricket there. Ah, here we go. This cannot be. Do you remember this group of cells added up to 17? Because we have 18 there and 10 here, that's 28. To get to 45, these are 17. If this was a 3-6 pair, what goes on the arrow? Not 3, 5 or 6, 2. It would have to be 1, 7, but that's impossible because 7 is limited in the central box. So this is not a 3-6 pair, and now we know exactly what they are. And that is going to finish the puzzle, I think. We get 7, 8 and 2 there. The palindrome continues with a 2. 2 and 7 are done here. Now, this arrow, it's either 1, 6 or 3, 4, forming a quad with those. And these become 2, 5, 7. And these become 1, 3, 6. And that palindromic cell is 2 or 7, but its C's are 2, so it's 7. 7, 7, 7, as Monica Geller would say. Now, this pair can't have a 7 in. So it's either 2, 6 or 3, 5. That's still not quite resolved. 7 is looking at this circle cell, so there's no 5 on the arrow. 8 or 9 there. That's not quite a pair. This is a 1, 3, 6 cage, and this cell can't be 4 now. That's 1, 3 or 6. So the 4, 8 pair is very fixed. This is a 1, 3, 6 triple. We can't have 7, 1 in this cage. So it's either 2, 6 or 3, 5. This digit now is either 2, 3, 5 or 6, but can't be 2. So that can't be 2. This can't be 6. 9 is in one of these 2 cells. I don't think that's going to help. I'm not even going to pencil mark it. I do think we are flowing to a finish somehow still. It's odd that this 1, 3, 4, 6 didn't break down a bit better for me. 2, 1, 7, 9, 8, 4. No, I just don't know. I don't know how they work. 1, 3, 6. Oh, that is deciding this cell, the 1, 3, 6 triple. That's a 5. Right. So we get 3 there. Now there's lots of cells that can't be 3. And that's become a 2 in the center of the puzzle. This can't be 3 anymore on the palindrome, so we've placed 3 in the central box. That sorts out 1, 3 at the top. That makes this a 2, 9 pair, which probably aren't resolved yet. The rest is Sudoku. Goodness. Is it this row now? 5 and 5. We need another 5. That goes here. That stops this cell being a 5. Much more importantly, it stops this being a 5. So that palindrome is finished. We don't have a 6 in this pair now, which must be 4 and 3. That gives us 8 and 5 down here. These are now a 1, 6 pair. 5 has come out of these cells. Let's remove the corner marks. These are 3 and 5, and we know the order. That fixes 3 and 1. That fixes 6 and 1. That fixes 6 and 8. This digit is 4 or 9. 1, 3, 6, 2, 5. These are from 4, 7, 8, 9. Still not resolved. I still think this row might provide a bit of a solution at some point, but I don't know quite how. I'm looking for Sudoku. 3 is looking up to that cell. Sudoku is your only man. Right, 2 there. So this can't be a 2, but this arrow needs a 2, and we therefore place it. That gives me a 9. That makes this a 4. These are now 7, 8, 9 as a trio. What have we got over here in this column? That is 7 or 9. I don't know, something's happening here. 3 sees that cell. No, that doesn't resolve. 1, 4, 2, 3, 5, 9. This is 6, 7 or 8. How is this not absolutely nailed on now? I don't know. That can't be 9. This can't be 7. There's an 8, 9 pair. Right, so this digit is 4. That's 8, and this isn't. 4 is ruled out of those cells, and this is 4. In this bottom row, there's a 7, 9 pair has popped up. That's a 6. That's 1 on the palindrome, and 1 in the eye. This is now an 8 in the circle by maths. That's a 7, that's a 9. And we get the digits at the top, and in row 6, these are 3 and 6, and now we can do the 7, 8, 9 triple here. And there we go. Lovely. Cantor's Blue. Beautiful puzzle, Matteo 99, and very enjoyable. And a nice set theory break-in that I figured out. Yay me. and delighted to do it. Do join me for another one tomorrow. Absolute pleasure doing these puzzles, and we will see you then. Learn a bit about killer Sudoku and arrow Sudoku, and maybe sometimes even set theory. Bye for now.